And now for an example question. The rate of flow of water from a well diminishes according to this equation, where V is the volume in megalitres that has flowed out after T days. Alright, show that dV dt is always positive and explain why. Well, let's just think about the context of this question. We've got water flowing out of a well. It's not going to go back upstream and into the well, it's flowing out with gravity. And time is always positive, so T has to be positive here. We also need to read this part. The rate of flow is diminishing. So that means that the rate that it's coming out is decreasing. So maybe a lot of water is coming out in the beginning, and then less and less water is coming out of the well over time. All right, show that dV dt is always positive and explain why. Well, T is always positive because that's time. And we know that E raised to any number at all is positive. And it doesn't make any difference at all if we've got a negative there. E raised to a negative number is still just a very small fraction. So if E raised to any number is positive, then we have dV dt is 3 multiplied by a positive number, which is positive. Now, explain why. Well, we can explain why without algebra, and I think we've just done so. But explaining why this makes sense to the context of the question, I would say, well, the water is flowing out. And so even though we've got less and less water coming out over time, the rate might be going down, but it's still going to be positive. If the rate was negative, it would mean that water was going back upstream, and that just simply doesn't happen. So you'd write that out as a sentence perhaps as well. Okay, find volume as a function of time. Well, to find volume, we need to integrate this. Now I'm going to show you a couple of different methods to do this. One method would be to say, all right, obviously we need to integrate this thing. The three methods I'm going to show you are just going to be methods for doing the integration. So what we need is this. And we'll have a plus c on the end once we do the integration. Now, if you are used to doing your integrations of powers of E using your formula sheet, then you'll know that this is not a perfect question. What we would really like to integrate would be if we had the minus 0.02 down there, multiplied by E raised to that same number multiplied by T, because this format makes it a perfect question. It means that we can look at our formula sheet and say we've got f dash x down the front, and then E raised to some function of x, or function of t, if you like, here. Now, that's not the question I was given. I've changed it, so I need to put a fixed factor out the front to adjust for that, give myself some room. I was given a 3, so that needs to be put back into the question, and I've gone and multiplied by something that wasn't in my question, so if I divide it by that same number, I've fixed it. See how these parts will cancel, and now the 3 is here, and I've made it the same as my question. Now, this constant here comes along for the ride, and I need to just get the part that's E raised to some function, and that will be my answer, plus C. Now, you can put this bit into your calculator and see that you get minus 150 E with all the same stuff on the end, and it's done. Now, this was quite a slow process, but a lot of people are going to like this method because it just avoids any mistake. It makes it really clear, this is what I need to do, this is what I'd rather do, this is how I adjust for it. I guess at this point here we could really have cut straight to the chase and put this part in our calculator. That would have made it much quicker. Put that in your calculator, and then you've got the answer to this part and your plus C. Now, another way to think through the exact same process is to say, look, I know that when I differentiate or integrate anything that's E raised to some function, I always get E raised to that function in my answer, no matter which way I'm going. So let's write that down, because that's the part I know is going to be in the integration. We'll write down the plus C, because I know that will be in there as well. Make sure I don't forget it. And then let's do the hard part and think about what needs to come out the front. Now, if I differentiate this, I should get back to that, right? And I know that differentiating involves bringing this negative 0.02 out the front. But I don't want it to be out the front when I differentiate, so that reminds me I'm going to need to have it down the bottom of a fraction so that when I differentiate this, it would instantly cancel. but I'm also going to need a 3. And then a quick inspection, because every time you integrate, you should always differentiate what you have to check it takes you back. I can see that this negative 0.02 will come down the front, it will cancel instantly, the 3 will stay there, and I'll get that. So the exact same working, if you like, but maybe a different thought process to get there. And on the next line, of course, you can put in the first part to your calculator and end up with the exact same line. All right, now we need to go back to our question and think, have we finished? Have we found volume as a function of time? Well, not quite. We've got this embarrassing plus c on the end. It's good that we thought of it, but we need to work out what c is. So we need to know the initial condition. Think about what V means. It's not the volume of water that's in the well, it's the volume that has flowed out after a certain amount of time. So when we began this experiment, or when t was equal to 0, no water would have flown out yet. So that means we can sub in when t equals 0, when t equals 0, V equals 0. So therefore 0 is equal to minus 150. Now e to the power of, this is going to make this whole section 0, isn't it? And e to the power of 0 is just 1. So minus 150 times 1 plus c. Now adding 150 to each side, I can see that c equals 150. So now I've got a better formula for volume. I'm going to write it at the top here, my answer to B, because I'm going to rub this out in a moment. V is equal to minus 150 E minus 0.02 T plus 150. Now, you could leave it in that form. Later on, if we're using it for something else, it might be handy to have factorised it. I can see I've got 150 in both parts. So I'm going to factorise it now just so that I can see I've got 1, using this term first, minus e to the that. And now I've got 2 forms of it there that I can use for the rest of my questions. All right, how much water flows out of the well in the first 100 days? Now I'm going to get rid of all of this so that I've got a bit more room for my working. Well, for this I need to let t equal 100 and then find what v is. So when t equals 100, v equals, now I can use either version of this. I think this one looks easier to me. 150 multiplied by 1 minus, now 100 lots of 0.02 is just 2, and so I need e to the minus 2 up here. And that's the same thing as 150, 1 minus 1 on e squared. Obviously you can put it in your calculator either of those ways. And we are going to get 129.7, and this is in megalitres. And I've rounded it to 1 decimal place, so I'll write that down. Okay, part D says describe the behaviour of V as t approaches infinity. Well, as t approaches infinity, we need to consider this part of our V formula, the e raised to something part. As t gets really, really big, we have t multiplied by 0.02. Well, that's still really big, but it's a negative large number. So what this is approaching then is 1 over e to the power of infinity. Now, 1 over a giant number is as good as 0, isn't it? So it's approaching 0. So therefore, our volume is going to approach 150 multiplied by 1 minus 0, which is just 150 megalitres. So in other words, what does this mean? Well, as time goes along, the maximum amount of water that's going to end up flowing out of this well is 150 megalitres. Now, maybe the reason is that that's all that's in the well and it's not being filled up and it hasn't rained. Who knows? But we're approaching some limit. And that happens because with our exponential curves, we're often flattening off or approaching some limit in the future. E says find the percentage of the total flow that comes out in the first 100 days. Well, we already have the information we need for this. In the first 100 days, nearly 130 megalitres flows out. And we're told that as time ticks along, the most that's ever going to come out is 150 megalitres. So all we need to do for part E is put this number as a percentage of the total flow, multiply by 100, we should get somewhere around 86.5% to one decimal place. Now, if you round it off, always state the level you've rounded to. And the last thing says to sketch V. Now, this is going to be a really straightforward sketch. There doesn't need to be a lot on it. I'm going to do it here and just show you. I'd do it quite big if I was putting it in an exam or in my book. But if we're looking at V, here is our formula. I think this one's probably easier to work with. We know that when time was 0, and this is time, no water had flown out yet. So we know we're starting at the origin. We also know that as time goes along, we're approaching a volume of 150. And we know that we've got an exponential shape to our curve. So it makes sense that if we have an asymptote up here at 150, because we're approaching that but we'll never reach it potentially, then it's going to be something looking sort of like this. And that's really all that we need to have on our graph.